What's up, guys? It's Frozen Electronics. Hi guys, welcome to another episode of Frozen Electronics. I've learned a couple new things about my camera, primarily that the gain option was turned on to auto, and I tried turning it off and everything was so dark it looked awful, which leads me to believe that clearly I don't have enough proper lighting in this room. I've got my big overhead fluorescent lights, I've got my tabletop fluorescent, but those aren't really adequate for recording. Clearly what you need is good lighting and then turn the gain off. Turning the gain on, I'm assuming, makes it look grainier. It's probably not as good quality as it could be. But anyway, that's just a little aside. Hopefully the video will start looking better soon. Dave, over on the EEV blog, recently did a video about the Apollo launch vehicle digital computer, the LVDC, which is very cool, from the Saturn V rockets, which is very, very cool to see. I would love to see how that thing actually worked. I would love to see the whole thing working, but that's probably never going to happen. Maybe it's in the Computer History Museum, who knows. I have some old chips too, clearly not 60s old. This is sort of the beginning of integrated circuits old. I've got a couple cool ones, but the one we're going to look at today... Oh, the other big news is I got a wrist strap, and this is the sort of time when you want to be wearing it, when you're going to be handling very, very old ICs like this. So I guess I should hold it with the hand that has the wrist strap on. We're going to be looking at this chip, which is a Schematic. Of course it's focusing on me because it sees my face. And you can't read that. It's a Schematic DG200BP. At least I'm assuming it's a Schematic because of the logo. It was made in the 10th week, 1977, which is pretty cool. Not as old as some, of course, but this is, this is PDP era. What this is, if I remember correctly, is a quad analog switch. I'm pretty sure it's CMOS. As you can see, it's a ceramic top. We have gold pins. Very, very cool IC. Unfortunately, one of the pins has broken off. That's just the wear of time, I'm guessing. We'll take a closer look at it under the camera in a minute here. Okay, so our chip, as I mentioned, is a DG200B. I think ours is a BN or something, but it's the same chip. It's a monolithic dual single pole, single throw CMOS analog switch, which is quite a mouthful. What it is basically is just a dual analog switch. CMOS is, just so you know, the voltage levels it can handle. We're going to take a quick look at the pinout, which gives you a very simple overview of how it actually works. So we've got our ground, V-, and V+, which specifically says substrate on the data sheet. So your in, which is your control signal, is just controlling the switch between S1 and D1. That's it. How it does that is a little bit more interesting, but for our purposes, when we go upstairs again and test it, we're going to see if this switch action is still happening. Unfortunately, it's our pin 1 that's broken off. So this is mirrored on this side between S2 and D2. I can still make contact with that pin, but of course we'll just use this side to test it. Okay, well here's the schematic for one of the switches. Very, very simple. Forgive my schematic drawing again. This is my nice huge graph paper I just got. So over here we have V+, VL, which I'm not sure what signal that is because it's not marked on the pinout anywhere, so it must be an internal signal. In X, which is our control signal, ground, and V-. Now the in is diode clamped both to V- and V+, so anything over that or below that will simply get clamped to that voltage. So you can actually exceed the input voltages on this by quite an amount from what I remember in the data sheet. I think you can handle plus minus 44 volts or something, whereas the input, the power is plus minus 15 volts, whereas this can handle plus minus 44 or something like that. Again, forgive my awful drawing. Right here we have an N channel FET. Right here we have a P channel FET. I'm not clear on what type of FETs these are. The data sheet I'm reading is newer than my chip by quite a number of years, so I don't know if this is the same technology that would have been used in the 1977 chip, although I imagine it probably is very similar. We've got an N channel and a P channel FET. Again, those are both being gated directly by the input. Our drain, and this one is coming from VL. Interestingly, we have these, usually these two are tied together, or is it these two? But we actually have them separated out. And I can't remember the name of the other pin here, but we have the center pin, well, in quote marks, center pin going to V+. Then the I'm assuming that this is the source is connected to the drain from the P channel FET, which both go to the input of the level shift drive. P channel FET, again, gated directly. This is normally the what you see on a FET these days, is that pin and that pin will be connected together. Again, pins in quote marks, because they're just internal sections on the, they're just internal junctions on the actual silicon, and those are both tied to ground. Ground, interestingly, this diode does not go to ground. I forgot to sort of draw the little jump like that. Ground is only here, and again I made a little mistake, so there's sort of a dotted line there. These two are tied to ground, and then ground also comes into our level shift and drive, but other than that everything is V plus, V minus. So essentially this is just a switching mechanism that will either pull this to V plus or V minus, V plus or ground, based on the input. It's just sort of a fancy way of doing it. You could probably drive it directly if you were to build this out of discrete transistors, that sort of thing, but in this case they have these FETs in here, probably both as protection and both to ensure that the signal being put into the level shift and drive is a nice clean switching signal. Again, this is an analog switch, so the fact that they're using FETs in here shows, gives us kind of a clue about what's going on inside the level shift and drive. Again, there's no information on what's actually in this, although again it's probably quite simple. They're simply level shifting whatever you're putting in on the input, which again could be plus minus 44 volts, down to something that can be used to drive the final switching transistors over here. Again, this section in the middle powered by V plus, V minus ground. We move over here to our output. Again, I guess my FETs are a little bit better drawn over here. We have an inverter, which is interesting. What's happening here is the output of the drive is being tapped off to this P channel FET over here. And again, they're showing that these aren't connected, which is interesting. Again, I don't know enough about FETs to understand the significance of that. Same with this one. They're showing that center pin just left unconnected. Again, we'd usually see it connected to source, but in this case it's not, which I find interesting. Anyway, again, here's our switch outputs. This is the input that's being controlled, and it's coming back out over here depending on your drive signal. If you have the switch turned on, it'll be able to flow through both these FETs simultaneously. This is where the interesting switching comes in, and the reason that there's an inverter here. Let's say that we're getting a plus out of here. So that plus will come to our P channel FET. Positive voltage, positive current, pardon me, on the gate is going to turn this off. Again, it's going to get inverted, so we're going to get negative over here, and again it's going to turn off the N channel as well. So both of those are turned off. Now let's say we get a negative over here. Again, 0 volts or negative in this case, is going to turn on the P channel FET. Once that's inverted, we'll get plus, which will turn the N channel FET on. And then current's going to flow through both of them and out the other side here, which is interesting. And again, both of these are clamped both to V plus and V minus, and again, this one is clamped to V plus and to V minus. And that's about it. Very simple for the time, but again, we're talking 1977 design. So they had to keep it simple because they wanted them to work. They didn't want to have silicon problems, they didn't want a lot of returns, I'm guessing, and they wanted them to be fairly rugged. So now that we have a very rough idea of how it actually works, let's go see if it still works all these years later. Alright guys, as you can see, we have, let me just grab my tweezers. We've got the DG200 in here with the beautiful date code of the 10th week 1977. Right here is my little frozen split supply, as I call it. Of course, that's going to be upside down to you. It takes in a regular plus and ground, and then gives you a plus and minus with a virtual ground in the middle. This design I found online is a great way to buffer it. Of course, if you pull too much current from one side or the other, it'll unbalance it, but this particular layout really helps to prevent that from happening. If anyone's interested in how to build one of these, they're very, very handy when you're prototyping. For example, right now I'm putting in 16 volts and ground, and then of course I'm getting plus 8 volts ground and then minus 8 volts, which is really, really handy. So I'm running the chip at plus and minus 8 volts. I made a mistake in the last segment. I actually had it backwards. The input signals can only be from plus and minus 15 volts. However, the supply range can be anywhere up to 44 volts. And that's 44 volts difference between the positive rail and the minus rail. So you could have 22 and 22. So that was just a little bit of a slip up. Again though, that diode clamp is there in case you exceed that plus minus 15 volt range. Assuming that, in my case, for example, you're only using plus and minus 8 volts, the inputs, if they're greater than that, will just be clamped to your supply voltages, which makes sense. It's a good way to protect the inputs of the chip. Now, for the test. So the way this works is kind of backwards from what you'd think. If I connect this, this is the actual control pin, and I actually had it backwards. It's not pin 1 I'm missing, it's actually the one on the other side. So this LED over here is hooked up in series. So there's a jumper going from power to the input of the switch, then the output of the switch to the LED, then through the LED, through a resistor, and then to V minus. I could put it to ground, it doesn't really matter. The current limiting resistor in there is 4.7K, which is a lot. So putting it across the full 16 volts is actually not a problem. Now, if I connect this to positive voltage, the LED stays off. Why is that? Well, probably because of the block diagram showing that there's an inverter in there. But here we go. Dun, 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 dun. I have a resistor. I believe it's 470K. I just kind of grabbed one going to ground, and hey, look at that. It still works. So we're actually turning this internal analog switch on and off inside there by grounding this out. Now let me show you. We could actually put it to V minus. There's an interesting effect when we do this. When I pull the pin away, it actually stays off. Oh, I was doing it before. Might have been because I was touching it in a certain way. I don't know. But the switch was actually staying on a bit longer. So that's interesting. Now, the other thing I'd like to measure is that in the datasheet it claims that there is an on resistance of only 45 ohms. So, I kind of want to test that. So let's test it. Well, I'm probing the switch of the chip when it's off. Whoops. And the multimeter seems quite confused. I'm getting an initial reading in the many megohms, and then it just goes confused and it's switching back and forth. Now let's turn it on. Oh, I'm getting 60.2 ohms. Not bad considering how many years old it is. It's almost 40 years old. Oh, the resistance is jumping around a little bit. Probably because my multimeter pins are sliding the breadboard all over the place, but hey, that's not bad. I don't know how well you guys can see the screen there. Let me touch it. 60.34 ohms. Pretty low resistance for the time. Of course, now we've got switches that have, you know, milliohm on resistance, but it's all solid state. This is mostly solid state, actually. This was meant to switch analog signals on and off using a digital signal as a control. And there, when I let go and turn the switch off, I get this weird flickering back and forth between megohm and kiloohm. So obviously the reading is either unstable or it's not able to correctly read it because of a semiconductor junction or that sort of thing. Well, thanks for watching this quick little video about this amazing old little chip. 1977 to 2014, so that's what, 87, 97, 07, so 31, 2, 3, 38, well, yeah, 37 years. Pretty incredible that the chip still works and that the on resistance is still only 60 ohms. Originally rated at 45 ohms on resistance, but considering it's almost 40 years old, I'd say it's doing pretty well. Pretty cool chip. I do have some other chips from the same era. Stay tuned, because you'll be seeing those soon as well. Thanks again for watching. If you enjoyed the video, please click the like button and subscribe if you haven't already. And it really helps me out if you refer your friends, if you think they're interested. I mean, don't spam anybody, but if you know someone who you think might be interested in some electronics videos, the more subscribers, the merrier. And if you have anything cool you want to send me, which doesn't happen very often, but if you do, just give me a message on YouTube or send me an email, frozenelectronicsblog@gmail.com, or check out frozenelectronics.com, send me a message. Any of those ways will work. I'd be happy to take your cool stuff, tear it down, do some experiments on it. I sent Dave a message about the Saturn V rocket LVDC board. I'll have to see if I get it. Probably not. Mike's Electric Stuff really is a better candidate, but we'll see. Thanks for watching, guys, and see you again soon.